little bit in the morning today, okay, and then we'll proceed again. So there were some questions in the lab yesterday. So now you are more or less getting familiar with the topic, okay, and also with the lab, hopefully. Okay. So there are some questions which were there in the lab. That number one is, what is the use or what is the objective of having a course like this, and for training very large number of teachers also. So what one of the objectives is, of course, to become familiar with the topic of robotics. So if you are teaching robotics, then how are you expected to teach? What is the theory components involved? What is the textbook to be followed? And then what are the kind of experiments you can do? That is one, of course. The second part is that there is a general complaint that robotics is very expensive. Okay. Now what you see in the labs is that, at least for the lab models, it is not expensive. What has happened is sensors, actuators, controllers have become so cheap today that actually you can build your own robotic system, very simple ones, just for teaching, for demo, okay, at very, very cheap cost, maybe 5,000 rupees, 10,000 rupees. So if you know the forward kinematics, inverse kinematics, you can very easily build your own system. Okay. And students can build and they can understand better also. Okay. That is the second part. Okay. The third part is regarding research. We have not come to the research as yet. So we are still in introduction only. So subsequently, at the end of this week is introduction mainly. Next week, it will become advanced research. Okay? So in terms of research for masters, for PhD, what are the relevant topics? Okay? So that is what we'll be trying to focus on. Okay? So teaching robotics, developing labs, in terms of research for master's thesis, then PhD thesis, what are the topics that we'll be looking at? Okay? Now the other thing that was mentioned in the letter from MHRD or NASCOM is that it is supposed to be training the trainer. Okay, that is what is the. So what they feel is that most of the jobs were IT related now. Most of the jobs, TCS, Infosys, or whatever. Okay, but the next generation is going to become IoT, or cyber physical system, or maybe robotics and automation. Okay, so IoT is Internet of Things. Okay, then cyber physical system we have just explained. There is a human, there is a machine, there is some kind of cyberspace. The third is your robotics and automation itself. Now these three things have something in common, if you notice. What do they have in common? They have a sensor, they have an actuator, and they have a controller. So if you know these three things, you can actually switch between the fields very easily. Okay. So for example, in a car, for example, so if you look at the all the cars nowadays, they have a camera for back parking, or they have the sensors. So it is basically an ultrasonic sensor only. The sensors that we saw in the labs. Okay. So there is an array of ultrasonic sensors which is controlled by some controller. Okay. So if somebody knows sensors, actuators, controllers, especially somebody, I mean students, then it becomes very easy for them to move into fields. Okay. So programming enough is not enough today. Okay. What they feel is that you should have some hardware experience. And again, it is not scary that hardware is very expensive and it's very difficult. It's not. Fundamentally, it is one sensor, one actuator, and one controller. That's it. And they are connected in different ways. Whether it's a car, it's a washing machine, it's exactly the same, and it's very easy actually. So what we expect is in this workshop, okay, when you go back, you should be at least familiar with sensors, how to interact, how to interface them with basic controllers. We saw some controllers yesterday. There is a details on microcontroller class. There is a details on microcontroller lab. There are different kind of microcontrollers. Atmega is there, PIC is there, Nano is there, Pio is there, so many. But they're fundamentally the same. Okay, so the objective for you and for your students would be that they become training the trainer, or they become a little bit more familiar with the area of sensors, actuators, controllers. If you say IoT, it is sensor, actuator controlled over the internet. That is all. Okay, there's nothing different. So fundamentally, they are the same. So if you get the fundamentals, okay, and that if we can further pass on to our students, then it becomes very, very easy for them to get jobs. That is the whole objective. Okay. So fundamentally, in this week, we are going to focus only on fundamentals. When you go to the lab, please look at the sensors, actuators carefully. Okay. These are used everywhere. Everywhere means everywhere. Okay. And it's very easy actually. Once you understand the program, which is open source, it's very easy to interface any sensor. Okay. And that is the kind of people companies are looking at now. Even companies like TCS, they are looking for people who have some hardware experience. Means they can, because they are going in for things like home automation. Sounds big, But what they're putting is they're putting a sensor somewhere and controlling it using the internet from somewhere else. And they're calling IoT and they're selling all over the world, making lots of money. So if you can be familiar with simple things like this, then the job market is looking for people like this. Okay? So that is the whole objective of this program, and that is the way it has been designed. So simultaneously, we are having it here, then we are having in IIT Madras, Delhi, Roorkee, Guwahati is next month. Okay? So more or less the course structure, profile, everything is same. Okay? Some of the instructors are same also. Okay? So that is the whole idea. Okay? So please take the lab seriously. It's not difficult. People in mechanical engineering, they don't want to touch microcontrollers and things like that. Okay, that I know. But it is not difficult. Once you see the program, you run it by yourself, you will see that it's very, very easy, okay, to interface any sensor these days. Okay. So let's proceed with that. We'll just revise very quickly today morning and then proceed. So the textbook, copy of the textbook, have you got the textbook? So hard copy will be given to you. They are supposed to give it today. So the soft copy is here. Okay, so Introduction to Robotics by Craig. So soft copy is there. I'll leave the soft copy here. So if you want a copy of that, just copy it and take it. So all the lecture slides are also kept here, okay, in one folder. So you can copy it and take it. Okay. All the programs used in the labs also will be keeping here only. Okay. So you can take all the programs also. Okay. So a copy of the textbook is kept here. You can take a copy of it and use it. Initially, what I would suggest, those of you who are not familiar with this, you can just read some of the chapters, like chapter 2 is in 3D space has 6 degrees of freedom. Okay. What are the 6 degrees of freedom? You have x, y, z, x, y, and z, and there are 3 rotations, one rotation here, one rotation here, and one rotation. So it's 6. In 4D space, how many degrees of freedom it will have? How many degrees of freedom does it have? 1D is only one dimension, so it can have only length, so it has only one. In 2D space, you have x, y, so it has x, y, and one rotation, 3. In 3D space, it has x, y, z, so it has 3 translations, 3 rotations, 6. In 4D space, it has 10. How did you get 10? The formula is given there. But no, my question was not that. My question is that 10, if 4D is 10, how did you get 10? Obviously, you got it from using this. But can you physically understand what is that 10? Okay. And if you say 5, then it is how much? And if you say n, then it is half into a squared plus n. So can you prove it? No, it is not one increment. In 1D it is 1, 2D it is 3, in 3D it is 6, in 4D it is 10. So it is not one increment. One more of what? Yeah, so can you prove it? And what does it mean? Okay, so this is a challenge question. You can try and see that. So when we are going from, if n is the degrees of freedom of the space, we are talking of degrees of freedom here. Okay, if n is the degree of freedom of the space, then for a body in ND space, the degrees of freedom is half n squared plus n. It has that many degrees of freedom. So if you put n is equal to 1, you'll be getting 1. If you put n is equal to 2, you'll be getting 3. Okay. So, but why is it like that? Okay. So can you physically interpret that and understand why? Okay. So this has a difficulty level of 36. So it's not very difficult, but it's difficult. So there are a lot of interesting questions like this. So if you look at this, there is a question number, and then there is a difficulty level number. In all the chapters, it is like this. No, fourth dimension is fourth dimension. It is 4D space. Okay, we'll come to that later. Let's just So today what I intend to do is basically I'll revise DS parameters, then we'll go on to so rotation matrix and homogeneous transformation matrix was more or less clear, right? So what about DS parameters? You're shaking your head like this, like this. DS parameters was derivation of what? Okay, how to assign the frames is DS parameters. Okay, so that part may not be very clear, so I'll revise that. Okay, then we'll revise, then we'll go on to kinematics of Puma robot. Okay, so briefly to answer your question of 1D, 2D. So this is 1D. So this is 1D. So in 1D you can measure only length, right? So in 1D space you have only one dimension, let's say x. So it measures only in one direction, x or y, whatever. So this is 1 degree of freedom. 1 degree of freedom. In 2D space, so this is my x and that's my y. So the body can have an xy plus it can have a theta, which is this angle theta. Let's say this angle. So it is 3 degrees of freedom. Okay. So what is an axis? An axis is a direction in space. Okay, it can be in any direction. Okay. Now this is 2 axis, means 2 degrees of freedom or 2 axis. What is the meaning of this 2 axis? There is one axis here and there is another axis there. Okay, that's the meaning of xy. So we say this is my x-axis, that's my y-axis. So these are directions in space. And here, basically, the degrees of freedom are this point here can have an xy, so the position here, plus it can have a rotation about this x. So there is 3 degrees. Okay. Now something to note here is that this axis and this axis, in a way, are actually, we are denoting it like this, meaning x is in this direction, it is 90 degrees, and it is orthogonal to this, y is orthogonal to x. That is the way we are making our xy axis. Now if I say of 3D, then this is my xy, and this is my z direction, right? This is z. Okay. Now what is the meaning of this? This means that if you have a body here, okay, it can have x, y, and z, x, y, and z, plus it has 3 angles, 3 thetas. So that is okay. So it can have x, y, z, which is a projection here, and it can have 3 angles with respect to the x, y, and z. So it is 6, right? 6 degrees of freedom. Now again, going back, this is a direction in space. This is also a direction in space which is orthogonal. Now these are directions in space which are orthogonal to each other. They are all perpendicular, right? Now if you think a little bit, how did we come from here to here to here? It's like I have 1D here. I projected this in this direction, so it became 2D. So a line, if I project it like this, it becomes like that. This is my 2D now. Now how did I make this into 3D? I projected this. It became 3D. That's how it is going, right? So I'm projecting it along the axis which I'm adding. So this has been. So if I want to do 4D, can I add another axis? So I add one axis like this, another axis I'm adding my 4th dimension. So let's call this S. Now this S is this and this. That is the way we go from one DOF to the other one. Okay. So from here it is like this. I projected it this side, it became a square. Then I projected it along the other axis, it became a cube. Now I'm saying I have a 4th axis now. Now I cannot draw it because this world is 3-dimensional. So I can't draw it. Okay, so I don't have that luxury. We don't have that luxury. So I have another axis which is orthogonal to these 3 axes. We can have that. Okay. So if I'm going to project this along, okay, so I have a cube which is in 3D. I'm projecting it axis, which is the 4th dimension. Okay. So what will happen? Can you imagine? How did we come from here to here to here? I have 1, which means one line. I projected it that side, it becomes a square. So this is like this. Becomes a. This is 2D. Then I take my square and I projected it that side. This becomes 3D. Now I project it along the 4th axis. So in the 4th axis, my 4th axis like this. This axis is orthogonal to all these 3. I cannot draw because in 3D you can't draw 4D. Okay. But if I'm projecting this, the other end also is a cube, and in between they are connected. Why not? Why not? Why not? So these three are unit vectors. They are orthogonal to each other. You have one more axis, which is also a unit vector, which is orthogonal to all these three. Why not? And you can keep doing that and going to higher dimensional space. We actually have to go when we come to a little bit more advanced kinematics. We have to talk of n-dimensional space. Okay. It is orthogonal to these three, so those dot products will have to be 0. Now this is called the Tesseract. So this is a cube, this is a square, this is a line. So essentially how we are going from one space to another space, we are going like this only. Okay. So this is a Tesseract, which means that if you take any section here, what you'll get is this one. Right? If I take any section here, I'll get this one. You're reducing the space. Similarly, if I take any section, I'll get this one. Right? Anyway, let's not get into this. Yes. No. Yeah, so we'll come to that. For example, as we go along, just after here, that if you have a manipulator like this, okay, so this is my xy, okay, you have theta 1, theta 2, and theta 3. So the relation between this and that is given by x dot is equal to j into theta dot. We'll come to this later. Because to control this manipulator, what do you want to control? You want to control the end effector. End effector is moving in space. How are you controlling the end effector? You're controlling the joint velocity. So there is some mapping between the end effector velocity and the joint velocity. Right? Because at the control, we are controlling the joint, not the end effector. But there is some relation between this and that. So that relation is given by this. Okay. Now if you look at the dimension, if this fellow is n, if there are n links, if there are 6, 7, 8 links, okay, then you are going to a higher dimensional space. Right? So the dimension of this can be only 2, x and y. Whereas if we have more number of joints here, the dimension of this fellow need not be 2. It can be more. Okay. So all kinds of things will happen now. So you actually have to go to a higher dimensional space. Okay. When we talked of homogeneous coordinate, that is 4D space. It's not 3D space. Right? So as we go along, we'll see that why you need to go to a higher dimensional space. But this is an interesting question that you can actually think. Okay. Till here, thinking is okay. But beyond this, thinking is more difficult. But the formula is interesting. It is half n squared plus n. That is the way it goes up. So if you can prove it, try it. Yes, but you cannot draw it. It's even difficult to visualize that. So you have to make one more axis, which is perpendicular to all of this, and then on that direction. But when you say that direction, what is that direction? Anyway, so when we come to this, then we'll look at going to higher dimensional space and how do we draw. Okay, but this is an interesting question. You can, if you are thinking that this is very easy, it's not all that easy also. Okay, so this is just for that. Okay, let's proceed now and just provide a little bit of for DH parameters before we go to. So let us just revise a little bit, and then, so we talked about DH parameters has been done. So DH parameters. Now when we are assigning axis to each joint, okay, one way could be that I assign axis randomly. I put the z-axis, x-axis, any direction I want, and then I can do a transformation between one axis and another axis. You can always go from one axis to another axis. We have seen rotation matrix, homogeneous matrix. So actually, I can assign axis in any direction. But then what will happen is your number of transformations will go up. Okay? So there has to be a systematic way by which we can reduce the number of transformations. So if there is some way by which we can systematically assign axis such that the number of transformation comes down. Okay? And that is essentially why, so this person, Denowitz and Hartenberg, two persons, 1969, they saw that although in three-dimensional space you have 6 independent parameters, but you don't need 6 independent parameters to go from one frame to another frame. At most, you need only 4 if you assign your axis systematically. So that's the logic of this. That if I have 2 axes, what I mean a manipulator like this, I'm assign axis now. Okay, so I can, and the third y like that. Axis is axis, it goes in any direction, right? I can do it like this also. So x is z is here, x, y is there, x is here, y is there, and z is in this direction. Okay, I can do like that. I'm just assigning axis. Now I can always go from here to here. I can find the relation between this and this. I can always do that using homogeneous transformation matrix. But if I have to find relation between this and this, you would find that rotations, your number of transformations will go up. Why? Because first you have to align this fellow, you have to align this z with this z, then only you can find the transformation between the two. So first transformation that you have to do here is align the z this side, bring the z this side, bring the x this side, bring the y that side. So that is one transformation. Then you have to move this fellow from here to here. Okay. So the number of transformations has gone up actually because I did it like this. Whereas if I have a systematic way by which I assign is like this, then what will happen? Simply add the, because it is always about the z-axis only, right? So the number of transformations come down if you systematically do it. So DH parameters essentially says that if you systematically assign your axis, then the number of transformations required to go from any frame to any other frame is not 6, but is 4 at most. Okay, why 6? Whereas the 6 come from rigid body has 6 degrees of freedom. So to go from any orientation position to any other orientation position, you should need 6. But if you systematically do it, you don't need 6, you need only 4. Okay. So how do they assign the DH parameters? So the DH parameters are assigned the z-axis. So let's do it like this. We'll take a simple example before making it more general. So the z-axis is the axis of rotation. Rotation or very, very simple. If you just remember these 2 rules, it's extremely simple. Okay. The first is that the z-axis is the axis of rotation or translation. So in this case, the axis of rotation, first is this is planar. So the axis is all coming out like that. So this is my z0 and z1 axis of rotation. There is no translation axis here. So this is my axis of z2 and z3. Okay. So rule number 1 says x-axis is axis of rotation or translation. Okay. So this is coming out of the board. So this is a revolute joint. So my z-axis is z0, z1. This fellow is the base frame, doesn't move. The first one is put there, then second, third, and if there are more, 4, 5, 6 like that. X-axis between z. Okay. So x-axis is the shortest distance between z's. So which means that the first fellow can be anywhere. Now the shortest distance between z1 and z2 is this one. Perpendicular distance between them. So this is my x1. Second is this is my z2, z3. So the shortest distance will be x2. Okay. And this can be my x3. Okay. So there are only 2 rules, nothing else. First rule says x-axis is the axis of rotation. So in this case, rotation axis, I put my z's. Then it says x-axis is the shortest distance between z's. Okay. So it is the perpendicular distance between z's. So in this case, perpendicular distance between this is this. So normally it is along the link only. Okay. So normally it will be my z-axis is the axis of rotation. It will be along the link. The first x can be anywhere. The second one is along the link. It is the shortest distance also. Okay. Y-axis is not required. Why? Because the moment you put x and z, as per right hand rule, the y-axis is fixed now. Okay. So the moment you fix z and you fix x, y is not independent anymore. So we don't require it. You don't need to put y. Okay. Okay. So we have put our z-axis and our x-axis. Now there is only one condition that comes up in x is So this is a condition of separate condition of x. So if z's are intersecting, then x is perpendicular to plane of z's. Okay. So in this case, the z's are parallel. So this condition is okay. X is the shortest distance between the z's because they're parallel. Now, if the z's are intersecting, okay, then there is no shortest distance between them. In that case, the x is perpendicular to the plane of the z's. Okay, let's have a look at this example. So this is another manipulator system here. So if you can visualize this, so this is now this one has one rotation axis like this. This can rotate like this. There is a translation axis. So this fellow can go in and out. So it's a translation axis. Now there is a third axis here, which is a rotation axis. This was clear, I hope, right? X-axis, Z-axis is clear, no confusion. Here, what happens is there is one rotation axis like this, there is a translation axis like this, and there is another rotation axis there. So if I put my Z, Z0 and Z1 can come here, Z0 and Z1, axis of rotation is fine. So this is my axis of rotation. But the second fellow is axis of translation, so it is like this, and they are intersecting here. So this is my Z2. So now the Z1 and the Z2 are intersecting. Okay, and this is my Z3, axis of rotation again. So in this case, this and this are intersecting. So the second rule says that if the z's are intersecting, then the plane containing the z's, the x should be perpendicular to that. So I can put x0, x1, and x2 there. Okay. So there are only two conditions. So z-axis is axis of rotation or translation. This is translating. So if it is translating, the z is in the direction of translation. So when we say axis of translation in a prismatic joint, if you remember, we had drawn our prismatic joint like this. So this was my prismatic joint. So this was the prismatic joint, right? So in this joint, okay, this can translate up and down. So this piece can go up and down on this. It cannot rotate. So when we are saying axis of translation, what is the axis of translation? This is my axis of translation along the motion. Okay. So in this case, it's translating like this. If you can imagine, this can go in and come out. So this is my axis of translation. So this is my Z2. Okay. So Z2 can be this side or it can be this side. It's an axis. But important thing is Z1 and Z2 are intersecting. So as per the second rule, if Z1 and Z2 are intersecting, then X is perpendicular to the plane containing. So this is the plane containing the Z's. Right? So there are only two conditions. Z is axis of translation rotation. X is shortest distance. If they are intersecting, then Z is, if the Z's are intersecting, then X is perpendicular to plane of Z. That's all. So only two conditions are there. Okay. So either this or this, it will fall in either of them. Okay. So we assign our Z-axis and our X-axis like this. This is for a revolute system. This is for a revolute and translating system. Okay. Just two. Now, now we want to go from one frame to another frame. Now, how do we do that? So we see a more generalized case, and to what is the relation between one frame and another frame? So now we have a generalized. Let me draw a more generalized kind of figure. So the previous one was very nice, planar looking kind of manipulator. This is a, let's say, a manipulator in 3D. It can have any structure, any shape. Okay. So this is having any shape. So this one is having any shape. Now we assign our z-axis as per the rule, exactly the same rule. Z-axis is axis of rotation or translation. This is only rotating system. Okay. So this is rotation. My axis of rotation, let's call it Zi minus 1. Okay. And this is the next axis of rotation, Zi. So as per the previous rule, z-axis is the axis of rotation or translation. In this case, it is only rotating. So it's a rotation axis. Right? So we put our z, fine. So this can be I minus 1 I or I plus 1. It just means the previous and next. Okay. Now I put my x-axis. X-axis is here. Okay. So let's say my x-axis is this side, xi minus 1. Okay. The next xi is this side, xi. Okay. Now if x is this side, y will be that side. I need not draw y, but this is my y as per right hand rule. I can only draw the x and the z. I don't need the y. Now the question is, if I want to go from this frame to this frame, or from this frame to that frame, how many transformations are required? How many transformations are there? You can have a rotation transformation or you can have a translation transformation. There are two types only. So how many of those are required to go from any frame to any other frame in space? Okay. Now, because a rigid body has 6 degrees of freedom, it would appear that you need 6, but actually it's not 6. So that what the ds parameter is basically saying, if you assign your z-axis like this, okay, then the number of transformations required to go from here to there is not 6, but is 4 only. What are those 4 and how do we get it? So let's look at this very carefully. This axis is this side, this axis is that side. So if I want to, going from here to here means I have to rotate, translate, and align this with that. That's the meaning. Okay. So let's start rotating and translating. So first this axis is this side, this is this side. So what I do is I make a line which is parallel to this. Okay, so I draw this line which is parallel to this. So this I make parallel here. Okay. What I'm trying to do, I'm trying to align this axis with that axis. So first I will align the z's. So I can align the z by putting an angle of alpha. So this z I'm going to align like this and make it parallel to this by an angle alpha. Okay. Now my zi minus 1 has come this side. Okay, zi minus 1. Now they are aligned, they are parallel. Then I will move this fellow by a distance of ai. So the origin from here has moved there now. Now the zi is here, zi minus 1 is here, xi is this side, xi minus 1 is this side. Now the origin is here, the z's are parallel, and the origin is on this line only. Okay, so what did we do? First, I drew a line which is parallel to this. So I take this line, make it parallel here, rotate zi minus 1 by alpha, make it parallel. Then I shift the origin from here to here by a distance here. So xi and xi minus 1 will not be parallel. Z will be the same. This and that will not be parallel. They will not be parallel. This one. So here xi minus 1 is in this side, xi is in that side. There is still an angle between them. But the origin of this and the origin of this is on this line. Okay. So first what did we do? We rotated this by an angle alpha, shifted it by a, it has come here. Now, so alpha happened, a happened. Then next, your x's are still not parallel. You can see xi is that side and xi minus 1 is this side. So there is an angle here, which is my angle theta. So I rotate xi minus 1 by an angle theta and make it parallel now. Now the z's are aligned, the x's are parallel. Okay. So third transformation was theta. Okay. So alpha a theta. Now the origins are not same, so I shift it up by a distance d. Okay. So now what would happen is this origin will come here. The x's are parallel, the z's are parallel. So how many did we have? A, alpha, d, and theta. Okay. If you do not rotate and make them parallel in 3-dimensional space, you will not be able to find a distance. So first you have to make it parallel, because you can move. Yeah. So the logic being that when these two axes are parallel, then only you can talk about a distance between them. Otherwise you cannot, because it's in 3D. So if you have one line like this, another line like that, completely skewed lines, you have to first make them parallel. So this is one line here, another line here. They are skewed lines. So if I want to talk about distance between them, I have to make one of them parallel at least. Then I can say shortest distance. Right? That is the reason why you need to do this one first. Make them parallel, then move by a distance. Okay. Then next, again the same logic. If this and this are not parallel, then you cannot find that distance, because the lines can be in any direction in space. So we make them parallel, then I move by t. So it is one angle, distance, angle, distance. This takes care of the z, this takes care of the x. Y we don't care. So at most there are four parameters, alpha, a, d, and theta. Okay. So I will draw it again. So let's draw it again, because once you understand it, there is nothing difficult in that. So we have, let me draw it in, so let me draw it like this now. This is one axis. More difficult, more different. Okay. So we assign our z axis first. Okay. So I assign my z axis like this. So this is zi minus 1. The next one is, this is my zi axis. Okay. So now then I'm going to assign my x axis. So my x axis here is assigned xi minus 1, and the next fellow is xi. Now I want to align this axis with that axis. Okay, that means there should be no angle between x and z, and the origin should be the same. That is the meaning of alignment, right? So how can I do that? So what we see is that the xi is in this direction. Sorry, xi is here, and xi minus 1 is here. So I have to make this parallel to this first. Okay. So what I do is first I make it parallel. So I take this line and draw it here, and I make this axis parallel. Now zi minus 1 and zi are parallel. Okay, so I have moved by an angle alpha. Next, I'm going to move this. Once I made them parallel, I can find the shortest distance now. So now I find the shortest distance, and I move it like this to here. So okay, so the z's are on the same line now. Now next what we do is we see that the xi is xi minus 1 is this side and xi is that side. So if I want to move this up from here to here, I have to first make this parallel to that. Then I can move the shortest distance. So I make it parallel by moving by an angle theta. So this is xi minus 1 now. Now this and this are parallel lines. Okay. Once I get that, then I move this up by a distance d, which is the distance from here to here. Okay. So what we did, we made it parallel, find the shortest distance, move. Make it parallel, get the distance, and move. So we have alpha, a, d, and theta. So 4 at most. That means if you want to go from any frame to any other frame in space, in 3D space, we need at most 4, not 6. If we assign our z and x like this. Alpha maybe. It's an angle. This is an angle. That is the convention. So now you can say that it is up to you to say whether clockwise is positive or anti-clockwise is positive. That's the convention only. By saying that if I rotate clockwise, we normally take anti-clockwise as positive. Okay, so that's a convention only. So at most there are a, alpha, d, and theta. There are 4 parameters. Z is always axis of rotation. In this, x is the shortest distance between the z's. They are not parallel, so you can take it in any direction. Right? Only when they are parallel, then you can make shortest distance, not otherwise. This is a generalized case. This is a general case. This is a very general case. So at most, you can need only 4. You may need less than 4. It's not that you'll need all the 4 all the time. So for example, if it is planar and the z's are all pointing out, then your x is automatically the shortest distance between z's. Right? So this is a case where it is a very general case where this axis is pointing in some direction, that is pointing in some other direction. Okay? Yeah, so the rotation of this is just making it parallel, shifting, making parallel, shifting. That's all. Okay? But this is saying that you need at most 4 parameters. Okay? So we need 4 parameters to go from one axis to the other axis. So what we need to keep in mind is that So what we need to keep in mind is that parameters A alpha theta, the base is this is axis of rotation or translation, x axis is shortest distance. Okay. So these are the two things for putting an axis. The moment we put an axis, then we can find these 4 parameters. A is called the link length. Is very to remember is the distance between z's. Okay, A is the link length, which is the distance between the z's. So A is the distance between the z axis. So let's look at an example again before we. So this is a simple manipulator case. Okay. So first I use this and I use that rule for putting z. Z axis is axis of rotation or translation. There is only rotations here. So Z2 and Z3. Rule number 1, Z axis is axis of rotation or translation. Okay, done. Next, x axis, first x can be anywhere. X0 is here. Then it is along the link, shortest distance, x2, x3. That is also done. Then I have to find these 4 parameters. So A is the link length, which is the distance between the z's. So the link length is the distance between the z's. Now in this case, they are parallel. So this is simply this length only, because they are parallel. So A is called the link length, distance between z's. Alpha is called the link twist. It is the angle between z's. So alpha is called the link twist. If the z's are not parallel, then there is an angle between them. In this case, they are parallel, so it is 0. Okay. About x. About x. Okay. So this is distance between z's along x. This is along x. So A alpha d is the distance. D is offset between x's. So d is the offset distance between the x-axis, and it is measured along the z-axis. Okay. In this case, the x-axis are all intersecting, so there is no offset distance. Okay. So A alpha d and theta. So this is called the link angle, which is angle. Okay. So if you note, it is only x-axis and z-axis are playing a role, nothing else. A is the link length between the z-axis. Zi1 and in that case. Yeah, so in that case, they were not parallel. So first you have to make them parallel, then you can find a distance. But in this case, if you see, the z's are z0, z1, z2, z3 are all parallel. So the distance A will be just this length and this length. Right? So if I make my DH parameter table now, so if we make our DH parameter table, then our DH parameter table will come out as, so first let me write it like this, A, alpha, D and theta, there are 4 parameters. And these 4 parameters we can remember very, very easily. So this and this is related to z-axis. So this is distance between z, this is angle between z, this is distance between x, this is angle between x. Right? So we start off systematically by putting z-axis, x-axis, then I find A alpha d theta in this table form. So I write A alpha d theta. A is the distance between the z-axis, alpha is the angle between the z-axis, distance between x-axis is d, and angle between x-axis is theta. And I simply write it like this to remember 0 to 1, 1 to 2, 2 to 3. So that confusion of z I minus 1 and I is also gone. So it is just the axis 0, and this is between z 0 and 1. This is between axis 1 and 2. This is between 2 and 3. Okay. So if you go strictly by definition, this said zi minus 1 to zi along xi minus 1. Okay, so that causes a little bit of confusion. It is just the distance between the z-axis. That's it. If you remember that, that's enough. Okay, this is angle between z. This is distance between x, and this is angle between x. about x. So twist is angle between z along or about x. Okay. So if you look at this example, let's call this L1 and this length L2. So I just make this table, and just to remember, I write a alpha d theta. A and alpha are distance between z, angle between z, distance between x, angle between x. Here I write 0 to 1, 1 to 2, 2 to 3. This means between these two axes, and these two axes. So we always start with 0, then 1, then 1, 2, 2, 3, like that. So the first one is A, is the distance between the z axis. Now z0 and z1, where is z0, z1? They are the same axis. So there is no distance between them. So it is 0. Next is alpha, is the angle between the z axis. Again z0 and z1 is the same axis. So again it is 0. Now d is the distance between the x axis. Now x0 is here, x1 is here, they're intersecting at that point. So again there is no distance, so it is 0. Now when the link moves, what changes? This angle changes. That is my theta 1. So when the link moves, if you can imagine, if the link is moving, it comes here, then it goes there, then it goes there. So what has changed is this angle between the x1 and the x0 is changing. So my variable is theta 1 there, which is the first variable angle. Right? The second one is 2 and 3. Where is, 1 and 2. Where is 1? 1 is here, 2 is there. So z1 is here, z2 is there. Okay. So we start off with A. A is the distance between the z. So z1 is here, z2. There is a distance here. This is L1. So it's my perpendicular distance L1. Then angle between the z. Z1, Z2 are parallel. So there is no angle. Then look here, distance between x. X1 is this side, x2 is that side. They're intersecting at this point. So there is no distance between them. Yeah. What about the angle? Now when link 2 moves, what will happen? The angle between this and this angle, theta 2, will change. So my variable is theta 2. It is the angle between the x. Right? Now what about here? Here it is between 2 and 3. So where is 2? 2 is here, 3 is there. Okay. So what is the distance between the z? So z2 is here, z3 is there, and L2 is the distance, so L2. Then what is the angle between the z? They are parallel, so it is 0. And what is the distance between them? Distance between the x-axis, again x3 is here, x2 is here, they're intersecting here, so it is 0. And this is my theta 3. Right? So we assign our ds parameter, we assign our z-axis, x-axis, then I find my a alpha d theta, like this in this table. So this is the table. Okay. Now let us, so this was clear, I hope. This one is easy. So you can simply write this distance, angle, and then it's easy. Now let's look at axis which is intersecting. System which is intersecting. So let's take that whole example again. Okay. So this is the manipulator system. First of all, we should understand how it is moving. So when it rotates about this axis. That's the rotating axis. Number 2 is this fellow can move up, forward, and backward inside this. So there is the second axis which is here. It's a translating axis. The third. So the first thing that we need to do is to understand how this moves. So this rotates, this fellow goes inside out, that fellow rotates. Right? Now what do? We add our z-axis. So I put z0, z1. I put z2 this side. They're intersecting here. Okay. Now z0 could have been here, z1 could have been there, if you want to take this distance. Now just to simplify it, I'm saying that z1 and z0 and z2 are intersecting at that point. It will reduce one transformation to take it from here to there. Okay. This is just for convenience. Is here. Okay. Now we note that z2 and z1 are intersecting. Okay. So the x has to be perpendicular to the plane containing the z. So this is the plane containing the z. So x2 is perpendicular to that. So it's coming out like this. Okay. So for convenience, I put x1, x2, and x0, x1, x2 there. So here just note that the z's are intersecting, so I'm taking x perpendicular to the plane containing z's. Okay. Now I'm writing my a alpha. So x3 is x2 and x3 are here. Okay. So x3 could have been taken. Okay. So just I'm taking x1, x2 this side, so I'm also taking x3 this side. I'll just explain it when we do this. So between x, this is angle between x. This is 0, 1, 1, 2, 2, 3. Okay. The first axis z0, z1 is the same axis. Okay. So there is no distance between z, there is no angle between z, there is no distance between x. Now when it rotates, what will happen? Can you visualize this? This is a plane. Now this x is on this plane. So it's on this plane, it is perpendicular like this. So if I say x0 and x1, so x0 is like this, x1 is also like this on this plane. So when it rotates, what will happen? x0 does not move, but x1 moves. So x1 will rotate that side, or it will rotate this side, depending on clockwise or anti-clockwise. But it is on this plane. Okay. So x0 and x1 are on this plane. So when x rotates, it is going to rotate on this side like this, or it will rotate on this side like this. So the angle between x0 and x1 will change, and that my variable theta 1. Right. Now 1 and 2. So 1 is there and 2 is here. Now there is an angle between here. So z1 is this side, z2 is this side. So it has rotated clockwise about the x-axis by 90 degrees. Distance they intersect. So the z2 and z1 are intersecting, so there is no distance. Yeah, and z2 is this side, because it is this joint is translating. So if you think the z2 axis is actually fixed onto this one. Z0 is the base frame which does not move. Z1 is fixed onto this link, which is rotating. Z2 is fixed onto that link, which is moving. Okay. So this is minus 90. So this. So I'm taking convention clockwise rotation. Is so Z2 was this side. Z1 is this side. Z2 is this side. So it is rotated by 90 degrees clockwise. Okay. So what distance between x is 0 and this fellow is when a translating joint moves. I'll just clarify this a little bit more. There are three parts here. One part is this one, second part is that one, third part is that one. If you say in terms of parts, if they are links, they are separate. Then the first fellow is this one. Okay, this is my 1. Okay, and this is my 0 actually. In terms of links, they are all separate. This is my the second. This fellow is 2. So it is a long link like that. And this is my third, which is there. These are the 3 links. There's 0, 1, 2, 3 in terms of parts. So Z0 and Z1, I'm putting intentionally my axis here. Z0 and Z1, I put it here. X0, X1 here. Okay. Actually, Z0 is here. Okay, it's the base frame. But to simplify it, I'm putting this and this together there. Just reducing one transformation. But it is on this frame. Right. So when it's rotating, what will happen? The angle between 0 and 1 will change. Now Z2 is actually on this link. Z2 is here, and X2 is there. Right? So the Z2 and X2 are on this link now. So when it moves like that, what will change? So the full origin will go that side, it will come this side. That means the distance between X1 and X2 will change, if you can visualize. Right? So the distance between X1 and X2 will change. And when this fellow goes this side or this side. Okay. And that is the variable distance here, which is my d1. So in a translating joint, the distance, variable distance is d1, and this is my variable distance. Okay. So this is, there is no angle there, so it is 0. So just to clarify, this this is fixed onto this part, which is moving, and The third axis is fitted onto here, so this is just rotating, which is there. So there can be some angle, there can be some distance here, okay, or there need not be a distance. So the distance between the z-axis, this z is this side, this z is this side, so it's 0. Okay. So what is the angle between the z's? They are again the same, so it is 0. Right? And what is the distance between the x? So there is x3 here, x2 here. So we can put some distance there, okay, and call it L2. And the variable angle is theta 3. Right? This one, you just understand it where the axis is being fitted onto the link and it's moving. Right? So now this is what we get. Our this is one variable, this is one variable, this one variable. The 3 variables. Okay. So this you have to do it by yourself once, it will become clear. Okay. Otherwise, it will not become clear. Now, what is the point of making a DH parameter table? So fundamentally, we want to go from one link, from one frame to another frame. That's the whole idea, right? So from this frame, I want to come to this frame, then to the ground frame. So I need a generalized transformation matrix, which will take me from any frame to any other frame. Okay. Now the generalized transformation matrix will have how many parameters? 4, right? Because at most it can have 4. So if you make a generalized transformation matrix, yeah. So DH parameters textbook says it like this. Okay. That A is the distance between Zi minus 1 to Zi measured along x. But all you need to remember is the distance between Z-axis along x-axis. No need of putting subscripts. Okay. So if you just remember it like this, distance between Z, angle between Z, between x, angle between x. And when we're writing the table, we can write it like that. Okay. Then there is no confusion anywhere. L2 is the fixed length. So this again, this origin is fitted here, right? So when this link moves, what will happen? The origin distance between frame 2 and frame 1 will change. But the distance between origin 2 and origin 3 is fixed. It's a fixed link, no? So that is my L2 distance. That is not changing. Right? Now we have seen that there are 4. So this is the DH parameter table for the Puma robot. Maybe you can try it. Okay. This is the experiment in the lab also that we are doing for the Puma robot. So it has 6 axes. You can assign the axis, or we'll do it in some other class, and then write the DH parameter table. Now there is a generalized transformation matrix. How do we get this matrix? We basically get this matrix. We saw that in general there are A, alpha, D, and theta, right? So there is the first transformation we had was an alpha, then we had a D, sorry, then we had an A, then we had a theta, and then we. Okay. So this is one rotation matrix, translation matrix, rotation matrix, translation matrix. Okay. So if I write these 4 matrices and I multiply them out, I'll get that matrix. Okay. That's where this generalized matrix comes from. Okay. So I have first angle between z's by an angle alpha. I rotate it. So I have a rotation matrix there. Then I have a translation matrix. Then I have a rotation matrix. Then I have a translation matrix. So if I multiply all these 4, I'll be getting this matrix in this order. Homogeneous matrix, we do not reverse order because you are in homogeneous space now, not in Euclidean space. Okay. So the order does not change like rotation matrices. Okay. But it's a 4 by 4 homogeneous matrix. So what we get is in terms of these 4 variables, A, alpha, D, and theta. So you can see this also has 4 variables only, A, alpha, D, theta, each corresponding to this one. Now what do we do with this is, if I want to find the very quickly, let's finish off. So very quickly, if you finish it off, I'll just take the objective of this is, if you take our previous example like this. So this is my Z0, Z1, Z2, Z3. This is my X1, X0, X2, and X3. Okay. Then if I write my L1, L2, so if you write our DS parameter table, then it comes out as table. So this L1, 0, 0, 3. Manipulator, we just wrote it some time back. Now this is giving me the relation between the frame 1 and frame 0. This is 2 to 1. This is 3 to 2. So I want to come from this axis to the 0 axis. That's the objective. So how do I come? From 3 I go to 2, then from 2 I come to 1, and then from 1 I come to 0. So this means that I can find the relation between this frame and the 0 frame. 0 frame is not moving. So that means each of this will involve one homogeneous transformation matrix. So there will be 3 of them because it's 3 axes. So this gives me 2 and 1, 1 and 0. And if I multiply them out, then I get the relation between 3 and 0. So we will not write this by hand. So when we are writing a when we are writing forward kinematics, inverse kinematics, we normally will use a computer program, MATLAB or C or whatever. Okay. So what we can do is we can make this table, and then I can take one row of this table and put it into this matrix, the generalized matrix. So it will give me T01 relation between first frame and the 0 frame. Then I take T1 to 2, it gives me the relation between the second frame and the first frame. And then I can take, so this is 1, this is another one, and this is T2 to 3. It gives me the relation between 3 and 2. Right? So what I can do is I can take this row there. Then I take this one, put it there. And you get 3 matrices. Now, if I want the total one, 0 to 3, it is simply a multiplication of T0 to 1, 1 to 2, T2 to 3. Right? So what will this matrix be? It will be cos 1 minus sin 1, cos 1, 0, 0, 1, 0, 0. This will be 0, 0, 0, 0, 1. Okay. In fact, if you see two axes which are the same, then this rotation matrix is only this one, cos minus sin, cos. Okay. Similarly, here it will be cos 2 minus sin 2, cos 2, 0, 0, 1, 0, 0. This will be L1, 0, 0. This is 0, 0, 0, 1. So you can just take this one and put it in there, you'll get this matrix. Similarly, this fellow is going to become cos 3 minus sin 3, cos 3, 0, 0, 1, 0, 0. This is L2, 0, 0, 1. Right? Now, if I multiply all of them, it will become, I'll get 0 to 3. Right? So what the computer program can do, this is a matrix and this is an array. So I'll simply take this array, put it into that matrix, and then it will get this one. Then it will take the second array, put it in this matrix, in the generalized matrix, and it will get this one. Then it will take the third array, put it in the generalized matrix, and get that one. And then it will simply multiply this into that, and say this is the relation between the third frame and 0 frame. Right? So if you multiply it out, what you'll get is cos 1, 2, 3 minus sin 1, 2, 3. Then this is sin 1, 2, 3, cos 1, 2, 3. 0, 0, 1, 0, 0. This is always 0, 0, 0. This is 1. This is L1 cos 1 plus L2 cos 1, 2. This is L1 sin 1 plus L2 sin 1, 2. This is 0. If you multiply it out, you'll get that. Okay. Now, could you look at this and write that? Yes, you can actually just look here and write that also, because this is giving the relation, right? So this is the rotation matrix. This part is the rotation matrix. So what is the relation between frame 3 and frame 0? So frame 3 is rotated by theta 1, theta 2, then theta 3. So it's a cos theta 1 plus theta 2 plus theta 3. Right? Now, what is this? This is the distance in the x direction, y direction, z direction. So if you look at this fellow, okay. So this point is L1 cos theta 1 is this one, then L2 cos theta 1 plus theta 2 is this much. So it is this plus that, which is this one. In the y direction, it has moved by how much? It has moved by this much, which is equal to this much plus that much. So how much is this much? It is L1 sin theta 1, and this one is equal to L2 sin theta 1 plus theta 2, which is this one. Right? So everything is logically set. All you need to do is just understand how it is done. Okay, and there is nothing difficult or very complicated about it. So simply by looking at this also we can write that. Right? But that is how a computer program works. Okay? Okay, so let's stop here. For the Puma robot, maybe we'll try it some other time. We'll have a look at the kinematics. It's given in the textbook. You can actually assign the z-axis on the Puma robot, write the DH parameter table, then use the generalized matrix to get each of the transformation matrix, 0 to 1, 1 to 2, 2 to 3. And if you multiply all of them together, a very nice expression comes which looks very nice, like that. So it's not good idea by hand. So normally we'll use a computer program to do it. then we can do inverse kinematics and whatever. But understanding is very, very important, and it's very easy. There's nothing complicated about it. But you have to do it by yourself once. So the two examples I gave today, please, when you go back in the evening, try to solve it by hand. Assign the axis, and then get the DH parameter table.